So good evening all, and I welcome you all in the course on the disaster risk reduction. I am Dr. Ashutosh Bhardwaj, scientist engineer at photogrammetry and remote sensing department at IIRS. So the topic for today's lecture is the role of GPS and GNSS in the disaster management. So we have seen that the geospatial technologies has made our life very simple. We are able to work a lot of activities from our home nowadays, which earlier we have been doing by standing in various queues in the offices, waiting our turns. But in the online environment, we are able to do many activities, and many of them are geospatial in nature. That means it also requires the coordinates. So, in case of the disasters, when we will talk, the disasters cannot be fully stopped. However, the effects can be controlled or managed using various technologies. Like in the recent case of the COVID, we all have used the Arogya Setu app, and such a vast country like India, we are able to do the vaccination, and we have a foolproof record of how many vaccinations we have taken and so on. And based on that, we have done our traveling also, whether you are going by train, buses, or flights. So your records are there and get the permission on the basis of that. So all that is an example of geospatial technology where the location is also used. So there are databases where it is recorded that where how many cases has been found. And based on that, various models has been run. You might have heard about the model run by various institutions who are predicting the scenarios in the times to come. So the purpose of the disaster management is to reduce the potential losses from hazards and to assure prompt and appropriate assistance to the people who are suffering and undergoing the effects of the disaster. And this we would like to do in a very rapid and durable way so that with the minimum time we are able to rescue the people and reduce the losses. Now here three terms we are normally finding that when we are referring to the disaster, it is a serious disruption of the functioning of a community or a society causing widespread loss of life and property. Whereas the hazard, it is the probability of occurrence of a potentially damaging phenomena. And then the third term is the vulnerability, which refers to the tendency of things to be damaged by a hazard. So the propensity here refers to the tendency with what speed or how much damage it can happen to a community or a structure or a service or a geographic area because of a particular disaster. Now, when we come to the remote sensing, GIS and GNSS, what we can have in the cycle of the disaster management. So in the disaster management cycle, a lot of elements are there, like the early preparedness is there, then early warning, then risk, disaster, emergency, evaluation for reestablishment, reconstruction, national development, risk identification, investigation, mitigation, and then the early preparedness. So they like this cycle is continuing. And what role can remote sensing and GIS can play here? And in particular, the GPS, which is the topic of the today's lecture. So basically, the remote sensing can provide us an instant view, and it can provide us a pre and post scenario images, which we can usually utilize for our purpose. And then We can have the extent of the study area which has got affected because of the disaster, or where we have the responsibility, because maybe different administrative boundaries are there and different countries are also involved in some various scenarios. So those extent mapping and extent identification can also be done by the remote sensing. We have to know the land use, land cover, what type of terrain it is there. That also we get from the remote sensing. We need to have some landmarks, benchmarks for the identification actually, which are available from the topo sheets in case of the disaster and the survey which has been carried out. But sometimes these are getting damaged because of the disaster. So if we have the geospatial data, we can navigate to specific locations or the previous ground control points by the use of the GPS, that is the Global Positioning System, or the GNSS, that is the Global Navigation Satellite System, which provides us the PNT services, that is the position, navigation, and timing. We will come back to this topic. Then we have the digital elevation model from the remote sensing data. We can generate the ortho images or the ortho photographs, depending upon what we are getting. If we have aerial photographs, we can get the ortho photos. If we have aerial images or satellite images, we can generate ortho images and the maps. And in the today's environment of a smartphone and the pocket digital assistant or the tabs, we can have the APIs also running on them, which can help us in the case of rescuing or any kind of stage of the various operations on both the sides. The people, if they have some APIs with them, they can also utilize them. And in the rescue operations, the agencies involved, they can also use. So in this all, again, we need the geospatial data. Why I'm talking about it? Because see, any data which comes in the form of the geospatial data, it has the location information. So that means at certain stage, we have done the georeferencing. We have done the coding so that the data sets have some coordinate system. So the remote sensing, so it helps at all those stages. Now the data sets which we are already, I think in the first lecture we have covered, we have different type of data sets with the various spatial, spectral, radiometric and temporal resolutions. And based on that, various parameters can be derived or the models can be run for the specific purpose. Now, whenever any problem happens or whenever we run a project, basically, so basically disaster scenarios gives us a live project. Normally, we do not wish to encounter it, and we try to be prepared for it in early stage so that we do not have any issues later. But the questions what we face during this, some of these questions are starting from what, where, which, why, who, when, and whom, and how. So how we have to control the data, whom we have to contact, who has to be intimated, from where we have to get the data, what is happening, where it is happening, what is the status of that, how fast we can reach the site. So all that require a knowledge about the place, and the best way to act fast is to have a geospatial data. So again, the position comes into the priority. So can the timely availability of geospatial data avert or reduce the data? If we are adequately prepared, we have our models running, we know what is going to happen, when is it is going to happen, because in some cases it is known. In the today's advanced world, with the help of the remote sensing technology, we already know the position of the cyclone, we know what are the areas which are going to be hit by it and when. In case some of the weather parameter changes, then also we have the scenarios, okay, if it changes its path, what will be the due course? So in 1990s, as we have seen, we used to have lot of damages. But today, in the last 10-15 years, what we have seen is that the damages which are occurring because of the cyclone or many other disasters have reduced a lot. That has happened all because of the geospatial technology, where the GPS or the GNSS coordinates are actually in the background. They may not be visible because visible is the image or the program or the outputs which are available. But in the background, in the input data, the coordinates are there which are coming from some source. So at the coarser scale, it might have been coming from the topo sheets like the Survey of India topo sheets or the maps prepared by different agencies. However, when we are starting in the today's technological era of remote sensing, then we have some aerial datasets, UAV datasets, satellite datasets, which have been actually georeferenced using GPS. Either on the ground, we have taken the ground control points, or on board the platform, we have GCPs. That means basically we have the exposure orientation coordinates, which provides us the position of the exposure station in terms of the XYZ. And besides that, we also know the sensor attitude also, that is the omega, phi and kappa. So that provides the rotation of the sensors about the XYZ axis. So that is called the onboard triangulation. So GPS is always there somewhere in the background. If it is not there, as the case was there earlier, then we used to have some other estimates, such as from the topo sheets or maybe some other devices like the gyroscopes, accelerometers. So they were also being used in the earlier days. However, most of the things in today's environment, we have shifted on the GPS or the GNSS. So the disaster response activities also involve the warning, evacuation, mitigation, search and rescue operation, assessment, emergency relief, and so on. And if you will see closely all these activities, we will understand that we very surely need the location of the disaster where it has happened, where we have the locations of the rescue teams like the NDMA, SDMAs, state disaster management authorities, where are the closest airport, railway stations, bus stands, or other communication services for the purpose of the deployments or the hospitals. So all those things we have to keep ready in today's environment as a parameter for the preparedness. The better we are prepared, the more we will be able to face a disaster in a way that we have the reduced losses or the minimum losses. Now, why GPS or GNSS becomes a very compulsory requirement in today's disaster scenarios? The reason is that the GPS or the GNSS is able to provide us the coordinates in any kind of environment, and that also on the 24/7. So anytime, day or night, we are going to get the signals from the GPS, whether it is snowfall, whether it is rainfall, whether it is flood, whether it is earthquake, any kind of scenario is happening. We are being helped by the infrastructure which has developed over so many years, and a lot of countries has put effort into it. And especially we are going to use the Navistar GPS system from the USA, GLONASS from Russia, IIRS from India, and similarly many other systems are out there that we will discuss. So that is very clear now that the GPS has a great utility in the various stages of the disaster, and it helps us after the disaster also by taking us to a specific location. So that is the background with which I would like to start today's session. So now I have discussed something about the disaster and the role of GPS into the disaster, considering that you already know that GPS provides us the latitude, longitude, and height of the location above the datum. So now we will basically start the GPS lecture from its basic, so that if some newcomers are there, they can also understand the topic in a simpler way. So when we talk about the GPS, basically it's a age-old problem. Sometimes we refer to it as origin destination problem also, that we are at a location A and we have to reach a location B and we have to again come back to a location A. So many ways we have been doing that with the help of the celestial bodies like the sun, the daytime, and the moon and the stars in the nighttime. With the help of the different markings on the uh, mountains, trees, and this has been seen in various civilizations across the history. So initially we have been working with the mental maps from last few thousands of years, and we have seen that in the different civilizations, very well built up settlements have been found with perfect 90-degree angles for the roads, very well planned ventilation systems, very well planned drainage systems. So that means the surveying has been done from thousands of years actually. Maybe the latest terminologies has not been used in those days, but it has been done through a proper structure thinking of the mankind. In the times, recent times, where we have talked about surveying as a subject, we have discussed various instruments, developed various instruments in the due course, starting from the very basic chain tape to the advanced theodolite tachymeter systems and the latest total stations. So various surveying equipments have been developed, and in those series of developments, the GPS is another surveying equipment which has been developed with the help of the satellite-based navigation scheme. So ultimately, what the point we want to raise here is that in the case of surveying, we want to define a location with the help of some coordinate system in some terms, like the geographic latitude longitude system or the UTM coordinate system. So the same thing is being done by GPS also. So GPS is primarily a surveying equipment. We normally forget that because it is combinedly used with a lot of latest technologies like the internet, uh, web-based solutions, and so on. Now in this surveying, basically we are again using the basic classical methods of triangulation, and in case of GPS, we are using the trilateration. So that means in case of the GPS, we are using the lengths only, we are not using the angles. That is how trilateration is defined. So in this, we are making the triangles, we can say as we do the traverse in the surveying. So here we do the all computations with the help of the distances. We'll go into that further. So in 1957, when the first satellite was launched, that is the Sputnik by Russia, and later on in 1958, the first satellite by USA was launched, that is the Explorer series of satellites. So these has given new dimension to the thought process and the problems thereafter. So initially we were worried about that whether these satellites are in the orbit, their designated orbits. So we have been finding that out using the Doppler shift method. However, we found that in the due course, the datasets which has been accumulated, they have been useful in defining the shape of the Earth also. So with the help of these satellites and the datasets which were gathered, we were able to define new Earth flattening ratios, and we are able to define new datums also. Okay, so that is the contribution what came into the surveying with the launches of different satellites, particularly in the geodesy, where we are studying about the three-dimensional shape of the Earth. Similarly, in 1993, the least square adjustment, decorrelation adjustment, the advanced techniques were developed for resolving the ambiguity. So we will come to the ambiguity also, which basically is the integer value, that is the number of complete cycles of wave which the GPS signals have traveled from the satellite to the receiver. So the new techniques has been developed to reduce the error. So error minimization techniques were also developed. So in the current scenario, when we are using the GPS and we are doing a lot of mapping and using it for various purposes, such as the disaster management, we need to understand a lot of things so that we are able to use those data sets. So we need to have some understanding of the surveying, some understanding of the physics, geodesy, statistics, astronomy, electronics. So we need to have some basic understanding of these topics. Now, when we have talked about so many instruments which were developed in the surveying field, GPS is standing in a different queue. Why? Because all the equipments which have been developed earlier, they required a clear line of sight between any 2 points which are being surveyed. GPS is the only equipment which do not require the clear line of sight while we do the survey. So that means at the same time I can do a survey using a GPS in Kanyakumari, in Jammu Kashmir, in the West Bengal, and in the Gujarat, and in the central India also. And in the same project, I can process all the data. That is the advantage with the GPS. None of the stations are visible from each other, but still the data set can be processed. And that is how we form the GPS-based surveying network across the country. So the brief history of navigation is also there. So from the sun, moon, and stars, and from stone, trees, and monuments which were there, we developed various surveying equipments for the purpose of surveying and which further help us in the navigation. Then various instrumentations like the compass, gyro compass, radio direction finding. These systems also got developed because of the Cold War era, and the World War I and World War II has accelerated the development of these equipments for the Air Force, Navy, and the Army basically. And these were again developed further in the form of the long range navigation systems like LORAN A, LORAN B, LORAN C. So these were the systems which were developed by the defense agencies in the initial stages to help the defense. And later on, when the situation has eased out, such as the LORAN C is also being used for the commercial shipping industry. Similar solutions were developed by the Russian agencies also, like the Chaika. So this was also high frequency radio based systems, which help primarily for the shipping industry and for the ground movement also to its user. So particularly commercial shipping agencies has benefited largely besides the defense agencies. So the LORAN C and Chaika, they were tower-based systems like today's BSNL tower-based mobile services, what we are getting. These systems were also similar to that, however, different in terms of the infrastructure. These are based on very tall towers, and very few towers can be utilized for the purpose of the triangulation actually, because ultimately triangulation is only being done again. Then in the later stage, Omega and Alpha systems. So Omega was the first terrestrial tower-based navigation system, which was developed by USA and its friendly countries. So we have to know that there is a tower-based system which works all over the globe with the help of the US and the friendly countries, and similar system which is called Alpha. It was also developed by the Russia. So before the satellite-based navigation systems, there used to be tower-based, ground-based systems which used to assist us in the navigation across the globe. Of course, the beneficiaries were limited because the technology was with few nations only. But the GPS has been provided to everyone, so it is being used for the majority of the population for their applications and benefits. So once the GPS has come, it has come in the form of the handheld GPS receivers also. But before the GPS, which developed with initial operational capability in 1993 and final operational capability in 1995. There was a very important system that is called the transit satellite-based system for particularly helping the Navy of the US. It was having 6 satellites only, and a similar system called Cyclone was developed by Russia also. So Transit and Cyclone were the first satellite-based navigation systems which were developed during the Cold War era, and these systems in the times to come were replaced by the GPS and the GLONASS, which were global in nature. Transit and Cyclone were the regional in nature. So they were helping in the area of interest as per the requirements of the times. They were not being utilized for the global applications. So then we have a IGS, that is the International GNSS service, which was actually earlier International Geodesy service and then the International GPS service. As the technology gets improved, the terminology is also changed. So we have seen the time that through those receivers which were developed for GPS and the GLONASS, the technology has come into the phone. So GPS phone started into the commercial domain from 1999 onwards. And once the Cold War era has gone, the GPS and GLONASS can be received in the same receiver. So that happened because the US and Russia agreed to work together and share the codes. So from 2006 onwards, the global navigation satellite system, this term became more prominent. Then in the due course, it was thought that the tower-based systems are no longer required, so dismantlement of that started. But with the anti-satellite missile experiments, people understood that the ground-based tower-based systems are also required. So the Lauren C system was enhanced and the Chaika system was also enhanced into enhanced Lauren and enhanced Chaika system. The earlier system, Lawrence C. Chaika, they were giving an accuracy of the order of 180 meter or 200 meter, whereas the latest enhanced systems, they provide an accuracy of the order of 20 meter or so. Then the GLONASS, which actually was performing not properly after the disintegration of the Soviet Union, it also started functioning again properly from 2010 onwards. And in the same year, the Japan also started the development of the quasi-zenith satellite system for the navigation purpose. Now, the time has come when we understood that we need the satellite-based navigation systems also and the ground-based navigation systems also. So a company like Red Electronics brought out systems which integrate the satellite-based as well as the terrestrial-based navigation techniques. So it's a 6 centimeter long chip actually, quite small as you can see, and this kind of services are available in Europe and some other parts of the globe actually, where they get the satellite-based navigation as well as the terrestrial-based navigation services together in the same system. So they need not to carry the two systems in the single system, they get both the services. In the case of the India, we developed the Indian Regional Navigation Satellite System from 2013 to 16. We completed our configuration or the constellation of 7 IIRS satellites, and they are functioning very well. And currently we have 8 satellites in orbit, out of which 7 are fully operational. One has some timing issue. So we have full constellation of IIRS providing us services all across India and 1500 kilometers beyond Indian borders also. So even the SAR countries are also benefiting with the IIRS receiver. Then a change came as in the market that smartphones has come in every hand, and in the smartphone, the Samsung and Huawei, they brought the capability to track carrier phase measurements. So that means we get the carrier based solutions. So it has become very easy to get very high accuracy using smartphones itself. You need not to carry handheld GPS now. Because in the smartphone, you can get 10, 15, 20 signals also now. The initial systems which were coming, they were capable of receiving 5 channels at a time, but currently you can receive 15 to 20 very easily in the smartphone. And the Android-based smartphones, they are capable of dual frequency multi-GNSS chips also. They are available in the smartphones. So the time is really changing fast. And with the smartphones, we can use a lot of technology in terms of the portability of GIS software also within the smartphones, APIs in the smartphones, and these are also they are very helpful. Then in the 2020, BDO also completed. That is the third global navigation satellite system, which is by China. So now the scenario is like this, that we have 3 fully functional global navigation satellite systems ready. That is the GPS by US, GLONASS by Russia, and BDO by China. And the Galileo by European Union is also going to complete very soon. Besides that, the IIRS and QZSS are the regional navigation systems built by the Japan and India for their specific regions. Now, this slide specifically shows the ELORN system concept, which is the tower-based system for navigation or position finding on the ground. These are the footprints for the global LORAN coverage. This was regional in nature. Then US LORAN system towers are shown. And then the timing and frequency overview, where we can see that the satellite-based technology and the tower-based technology, they have been merged together. And then the Xiaomi Mi8 system, which came into market with the dual frequency GNSS for the first time. So now there are many such systems which are available, and smartphones are gaining their place in the market, providing very convenient services to the users. The IRSS services, that is Navig services, they are also available in a mobile and can be used Android-based mobile phones, because IRSS package is also provided in the level 29 of the APIs. And in the recent, as you have seen that in the case of the India, Map My India company has come up with the app for the Navig. So these can also be utilized. Now this Eurofix service is available in the European region, as I was telling, wherein the satellite-based navigation system and the tower-based navigation system both has been combined. Now the miniaturization of the chip for the purpose of IRSS has also been successfully done by various agencies, including the IIT Bombay, the collaborative program with the METI, that is the Ministry of Electronics and Information Technology. And we have systems now working with the IRSS signals in the smartphones. So that is the scenario which we have now in the terms of the systems and facilities available in the smartphones. Besides the rugged GPS systems, either handheld or geodetic in nature. Now this GPS provides basically the position, velocity and time. So let us please note it categorically that we are provided with velocity and time also, besides the latitude, longitude and height. So the GPS acts as a timing laboratory also, because it has the atomic clocks in place and which are capable of providing us very high accuracy. And the position, velocity, they are, and time, all are referred in a common reference system. So that we have to very clearly understand. Then the International Civil Aviation Organization is also a very important player into this industry or science as well. So they also have defined the definition of GNSS as per their purview, because they look after the safe flying operations and the standard operating procedures for the aircrafts for their movement across the world. So they see the entire system as an integrated system, and that is why their definition, I quote, goes like this, that a worldwide position and time determination system that includes one or more satellite constellations, aircraft receivers, and system integrity monitoring, augmented as necessary to support the required navigation performance for the intended operation. Unquote. So this is the definition of the GNSS provided by the ICAO. So it takes into consideration everything on the ground stations, aircraft, satellite platforms as an integrated system, and it terms it as a GNSS. Whereas in the beginning, GNSS, we were referring to a system wherein in the single receiver we were getting signals from more than one service like the GPS and the GLONASS. But now the system or the definition of GNSS has got much wider. So now we have a deep space atomic clock experiment also, because the space missions, they are going far distances away from the Earth and the signal takes a lot of time. So they are having experimentations for independent movement of the satellites and various missions in the due course of time, which will develop. We do not know exactly how much, how far, and how much time it will take, but experimentations are going on. So a miniaturized ultra-precise mercury ion atomic clock has been launched because the belief is that the most advanced nations are always those who navigate the most. So now we have, or we are not limited to the Earth itself, but we have gone to the Moon, Mars, and the satellites are going beyond the solar system now. So we need some atomic clocks which can guide the satellite on their own and need not to wait for the signal from the Earth. So such systems are under experimentation for the purpose of the navigation. This is just to share with you. Now, we have understood that the four systems are there: GPS, GLONASS, Galileo, and BEDO, which are providing us the PNT services. So these systems are capable of providing us a positional accuracy of the order of 10 to 20 meters, a velocity of the order of 10 to 20 centimeter per second, timing of the order of 15 nanosecond, 20 nanosecond as per the system. And these are referring to different best fit curves for the Earth. So the ellipsoids used in all the four systems are, as I was discussing, that we have four systems, and now these systems are capable of giving us an accuracy of the order of 10 to 20 meter in position, 10 centimeter per second in velocity, and about 15 to 20 nanosecond accuracy in the timing. And they are working in different ellipsoid systems like WG34, parameters Zemli, GTRF, and CGCS. However, the transformation coordinates are known. So finally, we get in a single coordinate system. Now, basically, we use a one-way ranging system wherein minimum 4 satellites are required to provide us the signal in a one-way ranging method and resolve these equations. Actually, one are the equations which need to be resolved. So in these equations, we have the X, Y, Z as the location of the receiver and B is the clock bias. So these four are the unknowns: X1, Y1, Z1, and similarly the other coordinates of the satellites. They are coming from the satellite signal through the ephemeris data, and P1, P2, the pseudo ranges can be computed by various methods, such as by multiplication of the velocity of flight with the time of travel, that is T2 minus T1. T2 minus T1 basically refers to the time when the signal starts from the satellite and reaches the receiver. So T1 is the time here and T2 is the time here at the receiver end. So T2 minus T1 is the travel time multiplied by the velocity of light. So that gives the range. Now the GPS signal structure has some code solutions which are provided by the CA code and the P code. And there are certain phase-based solutions which are provided with the help of the carrier waves, that is the L1, L2 and the L5, which is the latest carrier wave which has been added into the basic system, along with the L1C, L2C codes which are in the pre-operational stage and the military code M. So these are the codes which are currently under use along with the L1, L2, L5 carrier waves, whereas L3, L4 are also there, which are used by the US defense for the finding of the nuclear detonation anywhere on the globe. The L5 has added value into the system because it is capable for providing indoor applications, anti-jamming features are there, and safety of life signal capabilities are also there in the L5. This is a comparative table for the GPS. So this table shows the various services, their nearest and farthest distance from the Earth. So apogee, perigee values are there, inclination values are there, orbital planes, how many orbital planes are there? So in GPS 6 are there, GLONASS 3 are there, Galileo 3, BEDO 7. How many number of satellites are there? So like that, this table gives a comparative statement for that. And what kind of velocities with which the satellites are traveling in their respective orbits, how much propagation time they need for the nearest position and the farthest position. So it is 67 millisecond here and the 86 millisecond for the GPS. And when this propagation time is being passed, how much the satellite itself travels in the respective orbits. So like that, this table is highly useful for the comparison. Different generation of satellites has been launched in the GPS because the entire satellite navigation we look in terms of three different segments. One is the ground segment, which includes the ground stations, uplink stations, and then the space-based segment, which includes the satellites. And then there is a user segment. So we all are the part of the user segment because we use the services. So the 5 launches has been done for the latest Block 3 satellite also, and this Block 3 satellite is a complete new setup. It requires new hardware as well as new software on the ground and in the space also. So it requires about $6 billion, out of which $500 billion are spent for the highly secured software with cyber security, and it is capable of providing us 3 times better accuracy with 8 times improved anti-jamming capabilities. So Block 3 has a lot of enhanced features as compared to the earlier block of satellites which were being used. However, this block will take time for completion. Currently, we mostly depend upon the Block 2F, 2R and 2M satellites also, which are being operational. Block 3, first 10 satellites of Block 3 are expected to complete their launches and working, the startup of their working by the end of the 2023. Currently, 4 operational satellites are there in Block 3 out of 5 satellites which are there. So out of those 5, 4 has been operational now. The status of Navistar GPS on today's date, which can be seen from the Navigation Center website. These all are shared very transparently for all the agencies, all the 4 GPS, GLONASS, Galileo, and BEDO. All details can be seen respectively from their websites in a very transparent manner. Then I was explaining that the geometry of the satellites with which we are linked at the time of operations, that is also very important. If the geometry is such that the satellites are available from all directions with a widespread distribution of satellites, then we get a good accuracy because the uncertainties are less. Whereas if the satellites are skewed, then we get a poor dilution of precision. DOP is a parameter which refers to the quality of the signal. So DOP is very good if the DOP value is between 1 to 3. It is considered good if it is between 4 to 5, and it is considered fairly good up to 6. Beyond 6, we try to avoid to do the survey at that point of time. Or if we do the survey, then we can exclude that data later on while processing the processing software. So if we are using, if we are interested in the X, Y, Z and time, then we can refer to geometric dilution of precision. If we are interested in X, Y, Z, then we can refer to positional DOP. And if in XY, we can use HTOP, and for Z, we can use VTOP. As per our use, we can refer to the specific DOP. Then the GPS works in a right-handed coordinate system in the Earth-centric Earth-fixed coordinate system. So we are having the center of our coordinate system at the center of the Earth. What coordinates we get in the GPS depends upon the settings, what we do as per the datum and the map projection. So as per our requirements that we can do there. Now when we go for procurement or use, we can either use the single frequency or dual frequency or multi-frequency receivers. The bit old satellites, the receivers, they are capable of giving us an accuracy of 1 centimeter plus 2 ppm in case of single frequency, and 5 millimeter plus 1 ppm in case of dual frequency. However, the latest systems, they are having capability of giving accuracy in case of single frequency of the order of 5 millimeter plus 1 ppm and of the order of 3 millimeter plus 0.4 ppm in horizontal and 3.5 millimeter plus 0.4 ppm in vertical, if we are using dual frequency or multi-frequency. So the basic difference is that in case of single frequency receivers, the baselines can be of the order of 15 km. If we are going for larger study areas with longer baselines, then we have to use the dual frequency or the multi-frequency receivers. Receivers can also be classified as geodetic class receivers, mapping grid receivers, or navigation receivers as per the type of accuracy requirements. So for highest accuracy requirements, we need the geodetic class of receivers. Now different sources of errors are also there. So the selective availability, which was intentional deterioration of the signals, have now been stopped. So this first one is not causing any error now. Then we have clock errors, ephemeris errors, atmospheric delays, and multipath effects, errors. So these are also there which we have to tackle. So this is the kind of budget we have from these various sources of errors. And we can see that when we use a single standalone receiver, our accuracies can be a bit less. They can provide in the current scenario an accuracy of the order of 10 to 20 meter. In the earlier scenario, it was providing us an accuracy of the order of 70 to 100 meter. That is the error before 1st May 2000. But beyond 1st May 2000, we are getting higher accuracy of the order of 10 to 20 meter, and which has also further improved in the recent times. That also I will tell you. Now these GPS systems, if we use in the relative GPS mode or the differential GPS mode, where we have one GPS to compute errors having known location, then the DGPS system can be used to provide meter level of accuracies through the code solutions and millimeter to centimeter level of accuracies using the phase solutions. So these type of accuracies can be taken advantage while using the DGPS. And there are other methods also which have also come up, like the precise point positioning and other systems. So normally what happens, we use a mask angle so that the signals which are coming from the lower angles that can be removed from the computation so that we can get a higher accuracy. So that mask angle is also used in the computation. Selective availability, as I was telling, now it has been switched off. So from 100 meter of accuracy, we are now getting 10 to 30 meter of accuracy. So on 1st May 2000, this feature has been switched off, which was actually there for reducing the accuracy achieved by the civilian user earlier. Now atmospheric errors, if the baseline is long, then we have to use some specialized softwares. But if baseline is less, the commercial softwares can be utilized for the DGPS processing. Tropospheric errors can provide us an error of the order of 2 meter at the zenith to about up to 30 meters of error for the low elevation satellite. So these tropospheric errors also need to be corrected in the computation, and they are highly dependent on the temperature, pressure, humidity, and elevation of the satellite. So these we have to take care. These are contributed because of the dry gases and the water vapor along with the condensed clouds. Then other ionospheric errors are also there, which are highly dependent on many factors actually, and they could actually go up to a error of the order of 45 to 50 meters also. So that is why the P code has been put for the US defense on the L1 and L2 carrier waves, because as per dispersion theory, if we are putting same signal on two different wavelengths, the delays can be computed. So ionospheric corrections can be computed by the use of the P code, which is actually encrypted, and after encryption it is called the Y code. So a W key is used for the encryption, but this can be encrypted only in the authorized receivers. So multipath error is that when the signal, instead of coming directly to the receiver, it hits some other object and then it reaches the receiver. So this also has to be taken care. However, it need modeling or a specific type of antenna such as the choking antenna. Then signal obstruction also cause some issues. However, because large number of satellites are there, so we need not to worry about it. Most of the places we get adequate number of receivers. While serving, we have to also take care that we are away from the tall buildings or electric fences or electric wires. Ultimately, we are getting electromagnetic radiations from GPS also. Those signals are EMR only. So that's why we have to take care of the sources of EMR also. And then we have to take care of the human error also, because there is no bounds and limits of human error also. So we had to see that no such error is there. Otherwise, our values or computations can get any kind of error. So now we have understood that a standalone accuracy can be order of 10 to 20 or 10 to 30 meters error. Now the latest report, which has been released by the US agencies, it says that if we have a latest receiver carefully fabricated, the current constellation is capable of giving us an accuracy of 3 meters in horizontal and 5 meters in vertical. Okay, so this is the third level. First level was the scenario before 1st May 2000, so wherein we are getting about accuracy of the order of 70 to 100 meters. But then once the selective availability was switched off, we are getting 10 to 30 meter or 10 to 20 meter accuracy. In the current scenario, post April 2020, if we have a latest receiver, then we can get an accuracy of the 3 meters directly in the horizontal and 5 meter in the vertical for 95% of the time. But most of us, when we are using, because we are using a lot of systems which are a mix of old and new systems, so we can say our systems, we are working with 10 to 20 meter accuracy. Accuracy can be increased by using differential GPS systems, which uses a base station having known location and some rover stations. So it can be 1, 2, or 3 rover stations also. So minimum 2 stations are used, one for computing the errors and using those errors for the correction parameters for the roving station. Okay, so minimum 2 systems are used. So what happens here in this case, that we know the current location of the base station as XYZ, and from the broadcast ephemeris data, that is the data which is coming in the real time, we get the X prime, Y prime, Z prime. The subtraction of the known coordinates and the new coordinates provide us the delta X, delta Y, delta Z, which is used for the correction. Now this correction parameter can be used either in the real time through the satellite link or through the use of the modem or internet based link. So then it is called the real time solution. Whereas we can process the data later on also after doing the service. So that is called the post processed solution. So these two kind of solutions are available. So we can have radial solutions when we are using the 2 receivers, or we can use a 3 receiver based system, 1 for the base and 2 rovers at a time. So herein we can switch on 3 systems at a time. So once we complete the R1, R2 and base network, then R1 can be taken to the next location, R1/3. Then we can have a second triangle into formation for minimum required number of observations. Once that is done, then R2 can be shifted to R2/4 and so on. So like that, we can have a 3 system based survey also. So that will be more accurate. Very user-friendly softwares are there nowadays. So simply in the post-processing case, we have to download the rover data and the base station data, and we can process the baselines, which will provide us the coordinates of the rover stations. So that way we can compute the GCPs. Now when we have to slate the absolute accuracy of the GPS derived data, we use the satellite laser ranging. So satellite laser ranging tells us that in the absolute coordinate system, GPS is capable of providing 10 to 15 centimeter accuracy, but this is the absolute coordinate system. Okay. In the real world, when we do some application like the urban application or water resource application, we basically use the relative coordinate system. So in the case of relative, we can go up to accuracy of a centimeter or millimeter level also using the specific post-processing system, wherein we process and survey with particular SOPs. And this, when we are talking about centimeter and millimeter level of accuracy, then that is basically derived from the phase-based solutions. The code-based solutions can provide us a solution of a level of meter only. So primarily what we are doing nowadays is the use of the phase-based solution. So advantage with the differential we use the static survey and rapid static surveys for the DGPs, whereas for the utility mapping, we use stop and go survey. And for the mapping of the trajectory, we use the kinematic surveys. Then for the UAVs and the aircrafts, while the data acquisition is done through the various sensors, we use the kinematic GPS. So we finally get very high accuracy from the GPS of the order of few millimeters when we are using the phase solution. So that kind of accuracies we are getting, and we have a precision, that means repeatability also very high, 2 to 5 parts in 10 to the power 8. So we have a very high precision when we are using the GPS. Now besides the DGPS, we have other solutions like sometimes we are going to the remote areas where power is not there, so it becomes difficult to maintain the base station and the rover station both. So we can have a service from the service provider like the Trimble or the Leica or other service providers are there. So they will take care of the base station using their network, and they will provide the correction parameters to the rover we are carrying into the field. So direct correction parameters and the corrected coordinates we will receive through the RTX SV service, satellite vehicle service, or RTX internet. These are the two services provided by the Trimble, whereas the SmartLink service is provided by the Leica. Now, besides this PPP, we have a network of cores also, continuously operating reference stations across India developed by various agencies like Department of Space, DST, Ministry of Earth Sciences. A Survey of India has established the network in few of the states which are completed, and they are developing it all over India. So on full completion very soon, we are going to have about 900 plus cores established by Survey of India alone, along with few hundred cores established by other agencies too. So all over India, we are going to have a CORS network. Currently, we have about 300 plus CORS actively operated by various agencies in India. So currently also we have a very good network. This is the CORS station at IIRS in the Indian Institute of Remote Sensing campus, which we are operating. So because of the large number of satellites, at any moment we are getting about 40 satellites in our region. Then there is a GDGPS system established by US for their operations within an accuracy of 10 centimeter anywhere across the world. So this is a service which they are taking advantage, which they have established. The future is with the tracking and data relay satellite system TDRSS based augmentation service, which is called TAS. It is going to provide us an accuracy of the level of 10 centimeter or decimeter for locating the small satellites also, because large number of small satellites has been launched. So this TAS service is for that purpose. Besides CORS network, GDGPS, we have IGS stations also. So about 512 IGS stations are operational across the world with the help of about 200 contributing organizations. So as part of ISRO, we are also contributing stations into this. You can see it at igs.org. These are freely available data sets which you can process for highest level of accuracies, especially for refining your base station data. And once you refine your base station data, then with those refined values, you can refine your over station data set also. So basically, base station data should be refined with the IGS station data, preferably, because that is very convenient now. So in India, we have the IGS station at NGRI Hyderabad, IISc Bangalore, then ISTRAC Lucknow, which is operational, ISTRAC Jodhpur, which is operational, and then few more at Shillong, Dehradun, Port Blair, they are also going to become operational. So we are also going to have very good network of IGS stations in India. These are the different shapes and designs of antennas which we are getting. Now we will come to the Indian perspective. So IIRS, as already I have told, it provides the service within India and across a region of 1500 kilometers beyond Indian borders also. So even SAARC countries can take advantage of the satellite system which is developed by India, IIRS. It is fully independent system owned by India, developed with the help of ISRO under the Government of India. And it also provides standard positioning service and restricted service for the defined users. So it has 3 slots, 3 satellites in the geostationary orbit and 4 in the geosynchronous orbit. ICD, that is the interface control document, has already been released. Updates has also been released. So these can be utilized by the Android app builders. They can use the APIs which are available in the Android. Already some of the services are operational for the fishermen. The International Maritime Organization has already certified the IIRS signals for use in large part of the ocean from 5 degrees south to 50 degrees north and 55 degrees east to 110 degrees east. So this IIRS is fully certified by the international agencies, and under the ASPA satellite-based augmentation system, wherein we use the already established accurately surveyed points for rectifying the values in real time by various users, especially the aircraft users. Okay, so here the concept is that based on the surveyed locations, that is at the reference station, corrections are computed and they are uploaded to the geostationary satellite, and which further disseminate the correction parameters to the users. So the geostationary satellites are very important here to repeat and broadcast the correct signals. So such systems are used all over the globe by various countries over various continents. Various systems are operational as shown here. So in case of India, it is the GPS-led geo-augmented navigation. So in contrast to the IRSS, see, IRSS is a fully independently owned by India. It is our system, whereas Gagan is also our system, but it is a dependent system. So the basic feed into Gagan goes from the GPS. Now GPS is fully certified for the en route operations from 30th December 2013, and subsequently precision approach services are also certified from 2015. So we suggest that all the aircraft operators should use these services. These services are very specifically useful for shorter runways, plateau airports which are having short runways in the hilly regions. So there, this service will help us in very safe landing and takeoff operations. These are the ground stations for Gagan. So GSAT 8, GSAT 10 and GSAT 15, these are utilized for the Gagan services. It reduces the fuel consumption. It saves time because we are able to fly point to point, because we need not to depend upon the DMEs or the VORs while flying. Few applications have come for the social use also, like for Alzheimer patients, they have released the shoes which are GPS fitted. So these kind of applications are also there. So in general, when we fly between two airports, we depend on the VOR and DMEs, which are not regularly spaced and available everywhere. So we have to follow a zigzag path. But when we are using the Gagan services or the ASPA services, we can fly point to point. This is a GPS view because we get a coordinate for the point. So points can make a line and lines can make a polygon. So these can be helpful for creating the maps. So currently we have very integrated technology based solutions. We have GPS, mobile SIM based services are there, camera, GIS software also, inertial sensors are also there, modems are also there in the single system. Okay, now there are systems like the Smart Station, which is released by Leica, and similar systems are available from Trimble also, which has a total station along with a GPS. So this will help the engineers working in the field very much actually, because they have to push it, which refers to the average datum and the polyconic system. There are toposheets which refer to the WGS84 system, the latest open source series maps if they are using. So it helps us to integrate the various systems when we are working in the field without confusion actually. So now, as I was telling, in the Android system, in the API level 29, the INSS based packages are available. Other packages for GPS, GLONASS, Galileo, BEDO, they are available in the API 24. So these can be used for the building of the APIs. So in the photogrammetric process also, as well as the urban mapping or photogrammetry is concerned, the ground control survey is a very important part where we use the GPS or the GNSS for the triangulation. And based on that, we do the ground control survey. Minimum 3 points are required. However, we do a very good peripheral survey and the control survey in the center of the study area also to have a good control in the region. So to perform the aerial triangulation or the satellite triangulation. Thereafter, we can use, besides the GPS, we can use the inertial measurement unit also to provide us the attitude, omega phi kappa, for the photographs also and for the laser based systems also, LiDAR. So ALTM is airborne LiDAR terrain mapping system, and this is the digital camera. So like that, we can have combination of technologies also together, either on the UAV platform or aircraft aerial platform. Now this slide shows our application which we have utilized the Cartosat data and the DGPS survey derived GCPs. You can see the large part of the Himalayan region from the Dehradun to Chandigarh. This entire area has been surveyed by us using DGPS, and we have done the satellite triangulation for the Cartosat dataset. We have developed the various solutions for various purposes for tectonic studies and various other applications. We have developed the digital elevation model for the entire area. We have developed the ortho images, and these are used for various applications for watershed modeling, for geological applications. The open source datasets can also be utilized. So this was a simple application where the Kanata Dam datasets has been used, optical datasets, Google Earth multiple images, and the SAR dataset from the Sentinel that was used for mapping of the inundated area. So this is how some applications I'm trying to show. Then in the case of the surveying field, we need to know the geoid heights also, geoid undulation also we need to compute. So we have online geoid evaluation utility. So by entering the latitude longitude, we can compute the geoid undulation. So either we have the topo sheet from where we can get the coordinates, then we can compute the GPS coordinates using this equation. Or on the other hand, if we have GPS values, then we can compute the mean sea level coordinates, because n can be computed from the geoid evaluation utility. So these things also. And this exercise we have done for the EGM 96, EGM 2008, and harmonic equations are there to the highest degree. Okay, so these are very accurate. However, most of our dependencies right now is on the EGM 96 model, because the databases which are available, they are referring to the EGM 96. We have currently a lot of assimilated or fused DMs also available, like the marine DM and Earth DM. So how to use these actually, because we have a lot of data sets which are available. So which one to use for our application? So these can also be utilized or basically qualified. You can test these with the help of the GPS data. Which one is better than which? Because now this digital elevation models, they are becoming primary input for many applications, such as for environment, for hydrological applications. So digital elevation model need to be qualified. We need to know the quality of the DEM. So in that also GPS plays a very good role because we can collect the GCPs from that. So these are some of the sites where we have worked at Jaipur, Kendrapara, Dehradun, Chandigarh, Kalka region, and the Delhi site. Sometimes we are dealing with difficult situations, like when we are dealing with the islands. So we have large tracts of water with a small piece of land in between that. So we have surveyed Maldives also. So in such cases, we use artificial markers. So at the time of flying, we can use these artificial markers wherein we can do the GPS survey at the time of flying, and these can be used as ground control points, because otherwise the ground has no identifiable feature, because only sand is there and dense canopies are there. So there are no road intersections, no canal road intersection like that. So in that cases, we use the artificial markers actually. Recently, very good solution has come for the safety of the railways. So they have developed, Indian Railways has developed the Kavach system. So it is an integration of GPS, various electronic devices, accelerometers, RFIDs, as I was trying to tell in the due course, that these are various devices which are being integrated for the solution of the Kavach. So now we will exactly know that whether the two trains which are approaching each other, the two trains which are approaching each other, they are on the adjacent railway tracks or they are on the same track. So if they are on the same track, this Kavach system will save us from any kind of collision. So here also GPS plays a very important role. These are the various open source digital elevation models which are available for global applications and regional applications across world. And we have the merged DMs also, like NASA DM, Merit DM, Earth DM also. Whereas for the entire Indian region, we can use the Card21 DM. It's a very good DM which has been corrected also and available for free download at 30 meters from the Duvan website. Whereas NASA DM is also a very good solution for global applications. Whereas the quality of NASA DM is very high because they have taken best input from the best uh, solutions regionally. So what happens? Different type of solutions are there. So if on the whole we see the NASA DEM do not have a uniform accuracy all over the globe. It will, however, it will provide the best available in that region through the open source. So that is how NASA DEM is also one of the very good data sets which is available now. For the robotic data acquisition also, we need GPS sensors, IMU sensors for automated mapping and various applications. Big applications, because many applications are there now which are being there, and LiDAR has been integrated into the mobile also. So there is a time where we are seeing that there is a lot of applications, a lot of sensors are being integrated. So GPS is one of the critical sensor, because for any kind of positioning we need GPS or the GNSS. So for processing the data, we are using various softwares which are coming with the purchase of the GPS, like a GeoOffice, GPS survey, Spectrum survey,